Okay, now we will define what is called diffusion velocity. Okay, so now we will see what is the diffusion velocity. So they take the fixed law again. Okay, rho A V A, the net flux of A in the x direction, that is written as the mass flux associated with the bulk flow, rho mixture density into velocity of the mixture capital V into YA minus rho into DAB dya by dx. Okay. Now this equation, let us divide this by rho A, the density of the species A. So we can write left hand side as VA, species velocity of the A, and here if we divide by rho A, rho V by okay. So this if you divide, you will get just V, because this if you take this here, this is the mass fraction. So this mass fraction cancels. So you will get V. So that is the bulk velocity minus this term appears, that is rho DAB dya by dx divided by rho A. Okay. So now this is the velocity, species velocity VA. Capital V is the mixture velocity. So this should be a velocity. Obviously, that velocity I call it as the diffusion velocity of species A. V, small v, A, the species, comma diffusion. To represent this is diffusion velocity. Okay. So that is calculated using the product of rho into DAB and the concentration gradient or the mass fraction gradient divided by rho A. Okay. So here this diffusion velocity can be written as DAB. Now the rho by rho A can be written as 1 by YA. So DAB minus DAB by YA is the mass fraction of the species A into dya by dx in the x direction. So this is the actually one dimensional thing. So the diffusion velocity of species A is written as minus dAB by YA into dya by dx. Okay. So you can just verify the units, meter square per second for the DAB, mass fraction does not have a unit. Similarly here dya, mass fraction does not have a unit, divided by m, the x is m. So m square, this cancels, so it's meter per second, that will be the velocity, diffusion velocity. So this is diffusion velocity. So if you want to calculate species velocity can be written as sum of V plus diffusion velocity. So sum of, so VA is calculated as the mixture velocity plus the diffusion velocity. Diffusion velocity in a simple way can be calculated using the concentration gradient and the binary diffusivity. Okay. So in a binary mixture, it is very simple to use a binary diffusivity DAB like this, and you can do gradient can be in one. See here, this is one direction. If you want to extend this to multiple directions, just you have to calculate. Velocity will have 3 components in x, y, and z direction. So so this may be x, VA diffusion may be in the x direction. Similarly, you can have another component, say WA diffusion in y direction. So here the gradient will be dya by dy, or in vector form we can write this as here. Okay. In vector form, the fixed law itself can be written in this way. Okay. Rho A, the density of the species A, into small v suffix A is the species velocity of the A, and it is a vector. That means that it is resolved in 3 directions in a 3-dimensional flow, and the rho is the mixture density and the v vector is the mixture velocity vector, and into YA minus rho DAB into del YA, that is. So in this way you can write this. Now same definition you can apply and get the diffusion velocity vector of species A is equal to minus DAB by YA into del YA. So this is the so this is a very simple way of calculating this, but we can now add so the main thing is we have to first calculate. So, it is easy to calculate or measure the mixture velocity. Okay, you can solve numerically the Navier-Stokes equations to get the velocity, or if you want to measure, you can use any methodology like petard tube or PIV or anything to get this. Then next challenge is to get, so I need species velocity for conserving each species. Please understand that in a multi-component mixture, we need to conserve all the species, individual species should be conserved. So, then for that you have to form a governing equation which involves the species velocity. The species velocity, since we cannot measure that, we have to calculate that in terms of the mixture velocity and the diffusion velocity. So, we have to calculate diffusion velocity in a particular way. So, for example, now in a convective term of species conservation, the mixture velocity capital V will appear along with the diffusion velocity, okay, because for conserving each species we need the species velocity there in the convective terms. So, in a very simple form, okay, we can write the diffusion velocity as minus dAB by Ya into gradient of Ya. But if you see this is only for a binary mixture. When there are more than 2 species present, how are you going to do this? It cannot be as simple as what we have written here. Okay. Now, before going to the multi-component mixture, more than 2 species, let us see some other characteristics of diffusion velocity. So, for diffusion velocity, what we have considered in the previous slide is only due to ordinary mass diffusion. That means it has only concentration gradients, correct? The mass fraction gradient what we have written, that is only contribution, that is the only contributing factor there, okay. So, higher the concentration at one location, lower the concentration at another location, due to the concentration gradient the diffusion takes place. But please understand that if this is basically due to concentration gradient, but if you take combustion reactions etc., you will see the temperature gradients will be very high, okay. See, because we can see that the temperature zones will be concentrated to a particular small region in the flame, and when you just go away from the flame in all the either direction. So, for example, if there is a flame like this, so this is the flame. So, here the temperatures are very high in the flame, within the flame zone temperatures are very high, but if you go to this direction or this direction, the temperature reduces, okay, to the ambient value basically. So, the large temperature gradient is seen, a huge gradient of temperature is seen, okay. In several scenarios, say for example, in a compressible reactive flow, pressure gradients can also be very high, but not in normal burners. Normal burners and stoves, pressure gradients are not, they are negligible. But if you take say aerospace applications etc., so you can see that there the pressure gradients can also be, when the mixture comes at a very high velocity and burns and products leave at a very high velocity etc., then the pressure gradients can also be high. Similarly, so for example, if you take the if there are huge concentration of temperature and pressure, they will also contribute to what is called species diffusion, okay. If the species diffusion occurs due to temperature gradient, huge temperature gradient, then it is called thermal diffusion, or in or it is also called Soret effect, SORET, Soret effect, okay. If the diffusion takes place due to pressure gradient, then it is called pressure diffusion, okay. So, these are the two additional velocities, diffusion velocities which you will get. So, one is due to the ordinary diffusion, which is very common for any multi-component mixture, even it need not be a reactive flow, normal flow with multi-component mixture, but some temperature gradient may be there, small temperature gradient may be there. So, the temperature based diffusion can be neglected, but the ordinary diffusion is still important there, okay. If it is say it is like a just air flow, okay, wherever you measure the gradient concentrations, the concentration of oxygen is only 0.21 everywhere, maybe minor changes are there, then you need not even worry about the diffusion. But on the other hand, if there is a concentration gradient, if say two different fluids like say oxygen and carbon dioxide mix etc., even the temperature may be isothermal like 300 Kelvin. Even in that scenario, you need to add diffusion. Ordinary diffusion due to concentration gradient is added in all the scenarios, but the thermal based diffusion requires very high temperature gradient. Similarly, pressure diffusion requires a very high pressure gradient. Apart from this, unequal body forces per unit mass. So, for example, as I told you, if you take say methane has a molecular weight of 16, it is much less than the air. Air's molecular weight is around 28.85. So, products hydrogen converts into water vapor and carbon converts into carbon dioxide. Water vapor's molecular weight is 18, but CO2's molecular weight is 44. So, you can see species of different molecular weights are available. So, unequal body forces can be created. In again, this is not in every scenario. Okay, in some scenario, you can get unequal body forces can be prevailed in a mixture. So that will also lead to what is called force diffusion, body force based diffusion. So this body force based diffusion also can be added in some context. Okay, now this means the diffusion velocity what we are going to calculate the species velocity here will be dependent on the diffusion velocity due to concentration gradient. I put suffix x to represent that this is the concentration gradient based diffusion velocity. Similarly, diffusion velocity due to Soret effect or the thermal diffusion, where I put a T in the suffix to represent that is due to temperature gradient. Similarly, diffusion velocity due to pressure gradient P here I am putting here. Similarly, due to body force gradient, unequal body forces, we can have diffusion velocity. Okay. In several scenarios, the last two terms will be very low, you can neglect it. But in several like a very low speed, high diffusion type of scenarios, the second term, that is the Soret diffusion, will be very important. But in all scenarios, the ordinary mass diffusion is significant. So, the diffusion velocity is contributed by ordinary diffusion due to mass fraction gradient, thermal diffusion due to temperature gradient, pressure diffusion due to pressure gradient, and body force due to the unequal body forces, okay, due to per unit mass. Okay. So, how to calculate this? This is very important. So, we have already seen a simple way to calculate the ordinary diffusion, okay, that is minus dAB by YA into mass fraction gradient. So, that we have seen. Okay. So, how to calculate this? This we will see now. Okay. Now we will add the complexity of more than two species being present. So, here we have seen the complexity of the diffusion velocity, which is not only due to ordinary diffusion, temperature gradient, pressure gradient, body force gradient, etc. can also give rise to this diffusion velocity. So, we have to add up all these to get the net diffusion velocity of species A. Okay. That should be added to the mixture velocity to get the species velocity of A. Now, let us consider a multi-component formulation for the mixture with more than two components. It will work for two components also, but we will consider more than two components also here. Okay. Now, the diffusion velocity of each species, okay, is calculated by solving not one, a set of equations, and this is called Stefan-Maxwell equation. This is the equation. Okay. When you want to calculate diffusion velocity, we have to solve a set of equations. So, this is gradient of mole fraction of every species. So, if there are n species, then there will be n reactions like this. Set of this reactions will consist of n equations for n species. Okay. So, n reactions. So, gradient of mole fraction will be equal to, there are four terms here. The first term, this is the first term, this is due to the ordinary diffusion. You can see that you take any two species. So, we are trying to solve for the ith species here, ith species. So, I have to loop over all the species. So, J equal to 1 to n. So, n is the total number of species here, n is the total number of species in the mixture. So, J equal to 1 to n xi xj divided by this dij. This dij is the so Bij is the binary diffusivity of the pair Ij. So this is the fundamental property of any two species, okay, I with j, any j, correct. So that is what is substituted here, and you have Vj and Vi. So now you have to solve this. So let us assume only you are solving the ordinary diffusion, that is term unknown will be present, other terms need not be there. So you have to solve n equations to get the velocities. Okay. Now you can solve this together to find the total velocity. So now the second term here is the pressure gradient based diffusion. So okay, you can see this del P, the pressure gradient term here, and this is the mole fraction, mass fraction and mole fraction here. So that this term is solved. So just by pressure gradient you can use this. And the third term here is the body forces. F vector suffix I is the body force for the species I. Now please see that if the unequal body forces are there, then this term will be significant. Fi vector minus Fj vector will be significant. However, if the body forces are not so high, okay, then this term will be negligible. So the total term, third term will go out. So in several cases, the third term will not be useful. Similarly, the pressure gradients are not so large. Okay, so that is also going to be negligible for us. Coming to the fourth term, here the fourth term, this is the Soret effect or the thermal diffusion effect, where the temperature gradient is going to be the driving force. And we have used the binary diffusivity in the first term, ordinary diffusion. Here we are going to use dt, which is nothing but the thermal diffusion coefficient. So this is the thermal diffusion coefficient, and it has a unit of kg per meter second, kg per meter second, thermal diffusion coefficient dt. Again, we have to use correlations, some correlations, and it is not so easy to really get the characteristic value of dt. Okay, for any species I and j, please understand, based upon the species you have to calculate this. So this is a very involved set of equations. Okay, very involved set of equations, and it needs lot of computations to do the calculate the diffusion velocities. And in several cases, as I told you, second and third term are not going to be important, they are not significant at all. Even in say somewhat for example, if the temperature gradients are not so high, and for example you are dealing with a mixture where the it's a very lean mixture, or for example lean mixture, then the maximum temperature is say 1300, 1400 degrees centigrade, something like that. The temperature gradients are not so high. In such a condition, this fourth term also will drop out. But anyway, even only with the first term, this involves n equations to be solved, and this is not going to be practically possible. See, if you have a very small flame, modeling very small flame, etc., this calculation can be done. But if you have a huge combustion chamber, okay, where you have to do this calculation, it is going to be very costly. So it will be very involved calculation for us, solving n equations of this Stefan Maxwell set of equations to get the diffusion velocities. So however, once you get this diffusion velocity for all the species, then you can add it to the mixture velocity at any location and get the species velocity at that location. Okay. So this is very important. So multi-component diffusion, here we are trying to resolve all the diffusion due to concentration gradient first term, then due to the pressure gradient second term, due to the body force gradient third term, or the unequal body forces, then the fourth one is the thermal Soret effect. Okay. Okay. So in as I told you, in many applications the gradients in pressure and body forces are negligible. So the second and third term are negligible. Okay. Now it is very costly for us to do this Stefan Maxwell equation for all the things. So if you solve this set Stefan Maxwell equation, then you are solving what is called full multi-component diffusion. When you solve it, when you numerically solve any flame, basically model any flame and simulate it, then if you incorporate the solution of Stefan Maxwell equation in that, then that approach is called full multi-component diffusion approach. Okay, but it is not easy to do it for all the problems. It is for some set of problems it's fine, but not for all the problems. So we need some simplified approach. Okay, what is the simplified approach? Is here what we are trying to say is, instead of calculating the diffusion velocity directly for the ith species, diffusion velocity directly using the set of equations, solving it together coupled way, what we are trying to do here is, just like say, let us assume that if you take a species I will only consider a binary type of scenario here, like I is the species, first species, then all other species in the mixture just other than I will be the second species. So let us consider only a binary type of species here, species I isolated out, all other species except the I constituting a second species, okay, bulk species, second species. This binary diffusion coefficient is now defined as DIM, how the species I is going to diffuse into the mixture. So that is calculated by a simple algebraic relationship given here. DIM, that is the rate at which I goes into the mixture. Now I don't see individually I go into J, etc. Now I am saying the rate at which I diffuses into the mixture. So DIM is calculated using this relationship 1 minus xi, mole fraction of I, divided by sum of the ratios of xi by dij. Now here this dij is nothing but the binary diffusivity of a pair of species I and j. Now when j varies here, it should not be equal to I. You have to exclude the I here, because what happens if j equal to I, then dii will come and that will be equal to 0. So this the denominator will be 1 by 0, it will be infinity. So we will not be able to solve this. So excluding j when it becomes I, all other sum up, we have to sum up for all other species. That is, I am trying to keep all other species as a bulk species and try to get the diffusion coefficient of the I to the mixture. Okay. So when you calculate DIM like this, then the species velocity can be calculated in a simple way. So instead of solving n equations, the gradient of xj, xi equations, I am just solving an algebraic equation like this. So at a given point, we know all the mole fractions of all the species. Using that and binary diffusivity, taking any two pair of species, I can calculate dij. Then I can finish this calculation DIM. Once I know the value of DIM, then I substitute here Vi diffusion. This is actually this is due to the ordinary diffusion, will be equal to minus DIM by yi into gradient of ya. So now here, instead of DAB by ya, delta ya I put similar to this, I can put gradient of ya. Similar here, what I am putting here is minus DIM, which is calculated using this. I am taking the help of binary diffusivities of any two species, and that is summed up for all the species. So that I can use this as a diffusion coefficient for the ith species going into the mixture. So this is the way I calculate the diffusion velocity of the particular species I. Now thermal diffusion velocity can be calculated once you know d suffix t of the ith species dti, then thermal diffusion velocity Vi diff t can be calculated as minus dti by rho yi into 1 by t into gradient of t. This way I calculate it. So now the total velocity will be sum of these two, ordinary diffusion plus the solar diffusion, that will be total diffusion velocity, that you add to the mixture velocity to calculate the species velocity of I. Okay. So this is a simplified approach. Okay. where you don't need to solve this n equations like this to get the value of Vi. Here we are solving like this. Individually, first you calculate an algebraic equation using an algebraic equation dim, the diffusion coefficient of the ith species into the mixture, and based upon that you calculate the diffusion velocity minus dim by yi into gradient of yi, and thermal diffusion velocity is calculated using the thermal diffusion coefficient dTi. So, dTi by rho into yi 1 by t into gradient of t. So, this is the way you calculate and add these two to get the net diffusion velocity of species I at a particular point, that add to that the mixture velocity to get the species velocity of I at the particular point. Now, let us consider the first example. So, till now we are only dealing with the gaseous mixture. Within a gaseous mixture, how the diffusion can take place because of the gradients. So, for example, if air will be flowing in a say horizontal duct, and as a cross flow a fuel can be injected. So, you can see that how the fuel and air mixes. So, initially at the point of injection the fuel concentration will be higher, and it is first partially carried by the air, and it also diffuses towards the direction where its concentration is low. In several scenarios you can see that when the convection is higher and higher, then diffusion contribution will be lower, because the convection will take will be it will suppress the diffusion. So, example, if diffusion is trying to transport the species in the direction opposite to the convection, based upon the strength of the convection, this will be nullified. Okay. Now, let us take a problem where you have a liquid phase also, liquid phase, and how the evaporation is done, and how are we going to analyze the evaporation of a liquid surface. For that we will consider what is called as Stefan problem. Stefan problem is nothing but where you have a test tube of this cylindrical vessel, or test tube in which a liquid is present, liquid A is present, and please understand that the liquid is also fed at a very slow rate, which is the rate at which the evaporation of liquid A takes place across the interface. Okay. So, this is the So, evaporation takes place, this is interface, x equal to 0 is called interface, okay, and across the interface the liquid is converted into vapor, and the vapor escape to the gas phase. So, this is the gas phase and this is liquid phase. So, gas phase. So, vapors go to the gas phase. Similarly, condensation can occur. So, the gas which has vapor A can condense. So, now we are seeing the evaporation problem basically. So, that means that this the temperature here, say T infinity, I will say temperature here is sufficient enough to provide the energy to the liquid so as to evaporate the liquid. Okay. So, now one more important point is, when there is evaporation which is taking place, if you do not supply the fuel here, if you do not supply the fuel, then the surface or the interface will regress. That means the interface will come down. But what we are trying to do here is a fixed interface problem. That means the rate at which the fuel is evaporating, at the same rate I try to supply liquid A slowly, so that the level is maintained at x equal to 0. Liquid level is maintained at the x equal to 0, which is the interface point. Now, so consider liquid A maintained at a fixed height in a glass cylinder or test tube. Okay. Now, on top of this, two gases A and B flow. Please understand that gas A is a condensable gas, it is a vapor. Gas B is like a nitrogen, non-condensable gas, which flow across under non-condensable under ordinary normal temperature and pressure. Okay. Now, concentration of gas A flowing across is less than that of interface. That means YAI is higher and YA infinity is lower. That will only drive the fluid from this interface to the ambient by diffusion. So, that concentration gradient prevails in the same direction as the convection. So, how convection comes here? That is the liquid in a tube, and there is a flow which is in the slow flow of gases A and B, which is in the horizontal direction. But what we are interested in is the transport in the x direction. So, this is the direction I want to resolve the transport. So, now there is no convection now initially present, there is no convection initially present. So, how convection comes in, that is what we are going to see. Okay. So, concentration of gas A or vapor A flowing across is less than that of the interface, that will drive the A from the interface towards the ambient by diffusion. Now, following assumptions are invoked. First, steady state exists. Okay, how steady state can exist? If there is no supply of liquid, then the liquid surface will regress, it will fall down slowly as the liquid is evaporated. So, that means steady state cannot be there. With function of time, the level of the liquid will change. So, that means that steady state cannot be prevailed. Okay, now you can ask one question, that is a constant evaporation. Okay. So, evaporation takes place. So, how can you can call it a steady state? Because with time, no, the evaporation can change. Yeah, the rate of evaporation need not change with time. That is what this steady state assumption means here. That means if evaporation takes place, slowly the liquid also is fed to maintain the level constant here. If the level is maintained constant here, then the diffusion scale here 0 to L, that is also maintained constant. So, we can get steady state evaporation. Okay. So, you can say it is a quasi steady, that means that the dynamic evaporation is also happening, that is dynamically you can see that there are some transfer phenomena happening in the x direction, but it is happening at a steady rate. So, steady state exists, that is the assumption, first assumption made. Liquid level is maintained constant by supplying the liquid A at the rate at which it evaporates. So, that is the way we maintain the steady state evaporation. If we do not do this, then the evaporation will be unsteady. Okay, now, one more point is gas B, say nitrogen or oxygen, whatever. So, let us say nitrogen, okay, is insoluble in liquid A. Liquid A may be a fuel, say methanol or ethanol, alcohol, and liquid A will form its vapor, that is ethanol vapor or methanol vapor will form, and that will mix with the ambient gas, that is say nitrogen for example. In evaporation problem, let us consider nitrogen. We do not even need to go to the oxygen scenario where the combustion can take place. Now, what this assumption means, can nitrogen dissolve in ethanol or methanol? Yes, it can happen when the pressures are very high. Like for example, if you go to say 10 bar, 12 bar, 15 bar and 20 bar etc., based upon the critical pressure etc., there is a good chance that the gas in the ambient can dissolve into the liquid, and it can also vaporize, like it can also come out as along with the vapor. So, that means this dissolution, okay, is possible, dissolving of the gas into the liquid is possible at higher pressures, but we are not concentrating on that scenario, and this is a very simple open atmospheric pressure problem. Okay. So, gas B is considered as insoluble in liquid A. That is important assumption made. This will keep the liquid phase single component. If gas B dissolves into the liquid, then it will become a two component in the liquid phase. So, okay, what all this, okay, then fourth one also we will see, the stagnant layer of B is present in the column. Okay, what do you mean by stagnant layer of B? So, predominant flow of B is in the other direction. So, this is the x direction, the vertical direction is x here, and the horizontal direction. So, we can say the vertical direction is x and the horizontal direction let it be y. So, that is the frame here. So, in this, when I say stagnant layer of B in the column this 0 to x equal to 0 to x equal to L, that means that there is no velocity for B in this column. Okay. So, only by diffusion the B comes down in this. So, obviously, in a binary mixture like this, 1 minus YA will be equal to YB. So, you can very easily calculate YB. So, YB, since that is Yb which is present in this column between 0 equal x equal to 0 and x equal to L. So, that means that the layer is going to be a stagnant layer which has transported B due to diffusion. So, this is the fourth assumption made. Okay. So, how will you solve this problem?